Hello everyone, welcome. This is NLP Lecture 3, and we're going to be covering sequence to sequence and attention. So let me just make sure everything is working correctly. Cool, awesome. Alright, so we'll be working through Lecture 3, where it's attention. It says attention, and obviously open the attention notebook. Also, how you guys doing? Let me know, man. While this slow Jupyter notebook loads. There you go. Cool, just wait till... Hello. Yeah, it's a gorgeous day today, isn't it? I walked outside and I started sweating straight away because I'm not used to the heat. Cool, we're going to be doing some exciting things today. I really like attention, and like when you first hear about the concept, when you first read the maths, for me anyway, it took like a long time to understand it and to understand what was going on. But after I did understand what was going on, then I kind of broke down the intuition behind it. It kind of opened up a way of seeing like maths in a different way for me. So I'm excited to hopefully show you how you guys can really bridge that gap between intuition and maths today. Also, the window's open. I'm not sure about the sensitivity of the mic on my laptop, so if it's too windy, then yeah, let me know. Hey, I made this pun. Okay, I promise to pay attention. There'll be a bunch more of them coming up. 11k steps, jeez. When in lockdown, how'd you do 11k steps in lockdown? That's mad. Okay. Anyway, let's get started. So I'll start with a brief recap from what we did last week, and then talk a bit more about bidirectional RNNs. I'll introduce the sequence-to-sequence model, followed by introducing attention, and then we will implement attention in the sequence-to-sequence model. I don't think we have time for this today, but maybe if we do, we can get started on the transformer, but if not, then we got next week to do that, so that's fine too. Most important thing is that you guys are learning, so as normal, feel free to drop questions in here anytime, and I'll come back and check frequently. Okay, so last week we looked at RNNs, obviously, and these were two different tasks that we looked at. One of which was like a classification task, so we have a sequence and then we want to classify it. And the other one was a more language modeling orientated task, where we have the inputs and then we have a predicted output and we have a ground truth output. So every time step we look at the inputs and we make some kind of prediction about what we think the next token would be, and then the ground truth token, using the teacher forcing methodology, will be the input at the next time step. So here we start we tell our RNN that we want it to start generating a sequence. So it starts and generates a word, and then the ground truth of this word gets fed into as the input to the next time step. Actually, so we have access to this ground truth at training time, and this is what it's trained on. At test time, obviously, we don't have access to a ground truth word, so we'll just be using the predicted outputs, but we train using the ground truth outputs. Yeah, sure. That's what all the dads say. Okay, so just going to start with the standard imports. No need to run through that. Okay, and a brief recap on bidirectional RNNs, because last week we only looked at it in the context of classification, And the way it works for sequence-to-sequence problems is a bit different. So in the classification task, or setup rather, we have one RNN going forward and another RNN going backwards. And then we want to classify based on some encoding of the whole sequence. So in the forward direction RNN, so this is the forward direction RNN. When we get to witty, this HT here, this hidden time step, it incorporates the meaning of the whole sentence in to some extent in this hidden state, and this is what we use to feed to our neural network, which outputs a classification. So in this example, we have this forward RNN, which goes here. This is HT here, this dashed blue line. And then we also had a backwards RNN. So this backwards RNN starts with witty and tries to work out the context moving backwards. So what we end up feeding to our neural network is the last hidden state of the forward RNN and the last hidden state of the backwards RNN. So here we've encoded all the information of the sequence if we were to move backwards in time. So this hidden time step here is just a concatenation of the forwards RNN and the backwards RNN, and that gets fed into this neural network classifier. Okay, so there's another way that we can use RNNs, and this is the way that we'll be using it in this lecture. When we come to actually talk about where we would use this, I can break it down into more detail if you guys don't fully understand it from this description here. So now what we have is, again, we have a forwards RNN and a backwards RNN, but the hidden time steps are done on like the individual time step basis, right? So for the word this, we have the hidden time step, or the hidden time step is 0 is the concatenation of the encoding at this for this forwards RNN and the encoding of this backwards RNN, and the same thing for the rest of the sequences, right? So now we have multiple hidden time steps because in this sequence setup would eventually be using these hidden steps for our calculation when we get to attention. So right now, so I'll recap it when we get there, but I just want you to be aware that there are differences in the bidirectional RNNs based on the kinds of problems that you're trying to solve. So here, when we want to have when we directly want to use the hidden vector for each time step, this is when we would use this kind of bidirectional RNN. Okay, awesome. So let's talk about the sequence-to-sequence model. Actually, it's quite intuitive. And we'll run through an implementation of that. And I think you guys have all the knowledge you need to be able to do this already. So let's walk you through the architecture. So we've currently encountered classification tasks where inputs are variable length, and we can use RNNs to make these predictions. However, when it comes to text generation, the lengths of an output may also be random, right? So we want to generate a sentence given some vector. Which is what we'll do, and I'll talk about that more in a second. But we have a vector, and we want to generate sentences based from this vector. But the length of these sentences can be variable length, right? It could be 5 words, or it could be 10 words, for example. So using a sequence-to-sequence model is one way that we can do this. And a sequence-to-sequence model is essentially a model that just contains 2 components: an encoder and a decoder. And commonly 2 RNNs are used as the encoder and decoder. So the encoder, or the input, is fed into the encoder RNN. So we have the input here, and this produces a vector. So what we're going to do is we're going to have this this HT here. So this is going to be HT. Actually, I have another diagram for this, which I'll bring up. I updated it last week. So I'll show you guys. Okay, so this is the old diagram, and this is the new diagram. and this is kind of a bit more accurate as to what's going on. So we have the hidden time step from the forward direction being output by obviously the last time step of the input, and then we have the hidden time step of the first in the backwards direction, the first time step. So for this, so from here, which is fed into something which we call C. So C equals HT concatenated with, or forwards HT concatenated with backwards HT. So here C stands for the context vector, which is just that vector as I was talking about previously. Here we just have HT, but actually this we're in this bidirectional RNN setup right now. So we want to have this HT and this backwards H0, so forwards HT, backwards H0. The concatenation of the two is what this is actually meant to be. So this diagram is a bit misleading because it should incorporate information from this RNN set as well. So I'll modify this after the lecture, but if you guys want to take a look in this Seq-to-Seq, so last week's lecture, in the images folder, there's a actually I can copy this over right now, and Seq-to Seq place. Cool. So now we see this context vector, and this context vector is used as initialization for the first hidden state of our decoder RNN. So we have this this context vector and a start of sequence token, and our network starts generating what it thinks the translation of the input sentence should be, based on this context vector here. Okay, so this context vector encodes the meaning of the hidden of the sentence, and then we use this meaning vector, this context vector, as initialization to the RNN for it to start decoding. Okay, so a question for you guys: why is this a forward RNN? Can we use a bidirectional RNN here? Just give you guys until just a minute. Let's see if we get any answers. Okay, why do you say no? Why can't we use a bidirectional RNN? Yeah, cool, perfect. So we don't actually have access to any future information. So we're generating the information and the tokens we need on the fly. So there's nothing to go backwards through. Yeah, great answer. Thank you. Okay, so let's talk about the model. So as I said, we have an encoder and we have a decoder. And in the encoder, there are three layers. There's the embedding layer, which will embed the inputs, an RNN layer, and a linear layer. So if we want to have a bidirectional encoder, we can do this by doubling one of the dimensions. And the linear layer that I just mentioned is used to keep the dimensionality between the encoder output and the decoder input the same, because otherwise this context vector would be, let's say our RNN has a hidden size of 100, so each hidden vector is size 100. This context vector would then be size 200 because we're concatenating the forwards information and the backwards information. So we have two strategies. We can either have our hidden states of our decoder be of length 200, or we can have them be of length 100. If we have them be of length 100, that means that we need to get this 200 dimensionality in this context vector down to 100 dimensions. And so we can use a linear layer to be able to do this. Either approach is completely viable though. So there's no predictions going on with in a bidirectional RNN per se. So okay, so let's recap a bit. So let's say we have a movie review task. So similar to what we were working with in week 1 and week 2. So this movie was something blah blah blah. Now in the forwards RNN, we get to this last time step and we have a hidden vector. So this is HT. So this is the hidden state of the last time step of the forwards RNN. So we've moved forwards in time and we've got this HT. Now we do the same thing in a bidirectional RNN, but also in the backwards direction. So here, instead of starting at the word this, we start at the word witty and we move backwards in time. And now here we have a hidden state which incorporates the information from the backwards direction. So we concatenate the two together, and this becomes like our feature vector that we want to use for a classification task, for example. So then we feed that to a neural network and we get a prediction, and then we would get a loss for this prediction and backpropagate that through both the backwards RNN and the forwards RNN with whatever error signal that was given to us. And that's similar to what we're doing here. So we have this HT. So this is in the, I'll just open this picture up because it's a bit bigger. I'll zoom in here actually as well. Forgot to do that. Okay. So we have this forwards HT, which is taken from the last time step, and this backwards HT, which is taken from the first time step. So that is in this diagram, this and this, and we concatenate the two together. So that's in this case that's called C for context. So this is the concatenation of HT and backwards HT, and then this is fed as initialization to the decoder RNN. So there's no getting rid of any words. It's just an encoding of the sequence, one in the forward direction and one in the backwards direction, and the concatenating the two together. This, to answer this part, how is this used to construct the correct sentence? So here we're like, if you look, we initialize our RNN to a zero vector. So our first RNN is initialized with zeros, and then our second RNN cell is initialized with H0. So the output of this RNN, and this H2, this third RNN cell, is initialized with the output of H1, which is why this arrow is coming in. So what we're doing here is we're initializing this decoder RNN, the first time step, with the context vector, and the context vector is obviously just come from what I've described, so HT and backwards HT. Okay, I hope that clarifies some information. If not, when we take a code break, or even now, just feel free to ask a question or clarify if you want me to clarify anything. Okay, so I think this one is oh, come on, don't tell me this is saved again. Okay guys, I'll tell you what, we're going to take a quick 5-minute break. I'm going to run through this notebook and delete the code where we need to fill it in together, and then I'll re-upload it so we can work on it together. Now, if you are still confused about something, yeah, just ask and I'll clarify it, because there might be other people here who have who share the same confusion as you. Anyway, I'll take a 5-minute break and I'll come back and answer that afterwards. Alright. Cool, we're back. Thank you guys for waiting. Okay, so we get to the first part of our code. So let me run through this, and we'll take a code break. So yeah, last thing I was mentioning is or I walked through the linear layer, which is used to keep the dimensionality between the encoder output and decoder input the same. Okay, so obviously we have our class encoder, and this takes in an input dimension, embedding dimension, hidden dimension, number of layers, something called the pad index, a bidirectional flag, and a dropout value. So what we want to do is we have this variable called feedforward input dim, and we need it to be twice the size of hidden dim if it's bidirectional, as in yes, as in twice the input size if twice the hidden dimension size if it is going to be bidirectional, because we'll be feeding it. We'll have this self.ff linear layer, which will transform something from the last output of our RNN into something that we can feed into the RNN. So the last output from the RNN we can think of right now as being this context vector. We'll have to do a bit of manipulation to actually obtain this context vector, but that's what we can think of it as. So as I said, if this was 200 dimensions, we need to transform it to 100 dimensions to feed it into this RNN. And if it's 100 dimensions, we still want to run it through the linear layer, because we can. Okay, so then we have an embedding layer. So we take in the input dimensions, the embedding dimensions, and the padding IDX. So what we're doing here, which we've deviated from last week, is now we're training our embeddings from scratch. So we're not using like pre-trained word vectors like we did with glove last week. We're saying, okay, let's initialize all of our let's initialize this weights matrix as random, and we'll just update it during training. So we'll see what input dim is in a second. Can you guys think about what it might be just intuitively? And we have this padding index which just says, okay, if we come across like 1, then just initialize the vector for this particular word as zeros. We feed this to an LSTM, so obviously we take in embedding dim as our input size, and then we have the hidden dimensions as the obviously the hidden size of or the size of each one of these hidden vectors. The number of layers, which would just be 1 in this case, and dropout, bidirectional, and batch first is true. So our decoder is going to take something as input in the shape of batch H, where H is the hidden size. So if we use bidirectional RNNs, we will be returning something which is of batch size 2H. So we need to apply, like as saying, a transformation to reduce our encoder dimensions to batch hidden size. And this is going to be done by applying a linear layer followed by a tan H activation. This is one of the code cells that you'll need to fill in. So here's this one and this one so far. Now forward method, I've got to delete this, but we embed the input and then apply dropout. And I'm going to run through a live demo of this in a second. So just take it as given now. But what I want you guys to do is also reduce the dimensionality of the final hidden and cell state. Then with the decoder, I want you to initialize dropout, initialize the embedding layer, initialize the LSTM. Remember to set batch first as true, and obviously we don't want to set bidirectional as true here. Okay, and then run through the forward method of here. You might need to read the documentation to see how you can initialize the hidden in cell state. So take a look here and run the feed forward layer, run the output layer, and remove the one dimension from the output layer and return that. Okay, so this is quite challenging. I'll give you guys 15 minutes. Take this as given for now, and I'll run through this part of the code when we're back and after I've done the walkthrough. So the concatenation is just what we need to do to have this vector representation to feed to the decoder RNN. So if we didn't do a concatenation, we'd be feeding, we can only feed in one thing, right, to initialize the hidden state of the RNN. We can either feed in, or like, and what are these things that we can feed in, right? We could feed in forwards HT, but that won't encode information from in the backwards time direction. So we could feed in backwards HT, but that won't encode information in the forwards direction. So we want to encode information both in the forwards time direction and the backwards time direction. So the concatenation is one operator that we can use to say, okay, here is the vector for the forwards dimension, here is the vector of the backwards dimension, and we can just put these together in like a big vector and feed that in as the initialization to our decoder. Yes, it is. Cool. So I'll give a code break. We'll come back at 42 past. Sorry, 52 past. And guys, please check out the groups. There'll be people in groups, yeah? Go check them out. If you want help, talk to them. Get some collaboration in, you know? Like, it will help both your guys' learning. You'll meet some new people, and hopefully we can have some more engagement from everyone if that happens. Yeah, and just do that. Just click on groups here at the side. See what happens. But you should all be automatically assigned groups when you join, so definitely check that out. Hello guys, welcome back. So we had this nice question here in the interim. Guys, if you can post your solutions here while I answer this question, that'd be quite nice. So what are the differences between the NN module and the function module? So for example, when to use nn.tanh and when to use f.tanh. Yeah, so it's a nice question actually. And I think the kind of distinction that it comes down to is the context that you're using the code in. So right now you see that we're defining models and using like this nice object-oriented architecture or a paradigm rather, where obviously NM module is an object, embedding is an object, LSTM is an object. So I think when when you're writing code, which is this, in classes and in object, for me personally, it's nice to just see everything following the same paradigm. So I would stick with the nn.module in that case. Sometimes though, and with some code I've seen, especially when it comes to loss functions, which are functions themselves, and they need to work out some kind of distance or metric, then they use the functional variant because they don't have an object which they're working, which they're coding this function in. It is just a function itself. Awesome. I'm gonna check these answers in a second. The sun is just in my eyes, so I'm gonna sort that out. Okay, let's take a look. Alright, so the first thing I wanted you guys to fill in was this bidirectional flag thing. So whoever answered this self.ff, if you could also answer what you put in this if statement here, that'd be much appreciated. So you are right with this though. We're going to apply a nonlinearity. So we have a linear layer followed by nonlinearity. So we have the linear layer, which is ff input dim, which comes from this if statement here and puts things to hidden dim because we want to change everything to h. And then obviously we apply a tanh activation. Yep, perfect. So here ff input dim is hidden dim times 2. So if it's bidirectional, we want it to be twice the size. Otherwise, we just want it to be oversized hidden dim. And what was the x equals self.dropout embedding x? Yep. And hn equals self.ff hn and self.ff cn. Cool. Awesome. All right, so let's actually see what this hn and or what this code here means. Okay. So recall what we're trying to do from the encoder. We're trying to obtain this context vector here. We want to get this c, and we do this by having access to the last by concatenating the time step from the hidden state from the last time step of the forwards RNN and the last time step of the backwards RNN. So we need a way to get those last hidden states. So our LSTM, as we discussed last week, so we're running this RNN, which is an LSTM, and we get outputs, which is all hidden states, and then hn and cn. Okay, where hn is the contains the information from the last hidden state, and the first dimension here tends to index which last hidden state we're referring to, because in bidirectional RNN we have two last hidden states. So this would be one of the last hidden states, and this backwards H2 would be the other last hidden states. And if we have more than one layer, we have that many layer times the number of directions that we have in our RNN. So we only have one layer here, which makes our life a bit easier, and we have two directions. So what we want to do is we have this HN, which is going to be of shape 2 times batch size times hidden size, and we want to get out the last from each of this first dimension. So and our new HN is going to be the concatenation of we're going to use our new HN as C. So sorry, CN here stands for cell state, not context. This C stands for context. So we're going to build this context using our HNs, which are this. If it helps to think of it, you can also think of this as HT, just to align the same, so we have the same indexing here. Okay. So what is this? What does it do? All right. So the way I like to break these problems down, if I come across them, is code them up in terminal. So we will run Python and import torch. Okay, so we see we have a 3-dimensional or a rank 3 tensor here. So we'll say torch dot torch zeros, torch a range. Do it in NumPy because I know the NumPy syntax for this. So HN equals mp dot a range 24 dot reshape 2 3 4. Okay, so we do HN. We have this tensor, essentially, 3D array of shape 2 3 4. Okay, so we got 1 2 and then 3 down, 1 2 3, and then 4 across. All right, so let's see what this does. So HN of 0 to 2. So actually, I don't need these there, and this will say okay. So, and just to prove that that's the same as putting these blank colons there. Okay, so we see that we have the same thing. Okay, so this is saying for every so if you remember what slicing is, right? So if we have a list, we can use this 0 colon something else, and this will slice this list and give us like the first from the 0th element to whatever number that we had after this first colon. Now what this second colon does is step. So we want to say if we had a list of let's say list equals range 10 list, okay, and we'll just do the slicing example, so 0 to 6, for example, and this gives us 0 1 2 3 4 5, as we would expect. Now if we put another colon and we put a 2, what this means is do 0 to 6 but take every other step. So what I would expect to see is 0 to 4. Okay, cool, because we've taken 2 steps. So instead of on every second step, we will read, right? So we'll say get everything from 0 to 6, but do it in step sizes of 2. So we get everything from 0 to 6, and then we have a step size of 2, so it's 0 to 4. Okay. So what we're doing here is we want to take a step size of 2, but right, remember we only have this first dimension is 2, so we only have 2. So all it's saying is that if we had something which was 48, which actually might make a bit more sense here, so 48 and then 4 3 4. So you see something which is now 4 down, 1, 2, 3, 4, 3, and then 4 across. Okay, so if we do HN002, what we'd expect to see is every even thing of this first dimension, right? So this is 0, 1, 2, 3, and this is saying, okay, take a step size of 2, starting at index 0. So this is 1, so this is index 0, so we consider this one, and this is index 2, so we consider this one, right? So you see that we've, by using this 2, we've extracted out this array and this array. Now similarly, if we go for 1, we would expect to extract out, with a step size of 2, all the things at odd indexes. So this would be this one here, and this one starting with 36 here. Okay, so you can see we have 12 and 36. And then simply we're concatenating these together on the last dimension. So what this means is we can just try it out, right? So we want to have what is it, mp.cat or concatenates, mp.concatenate, cool, mp.concatenate okay, hn02 hn1 2, and then axes equals -1, and we can see here what we've done is we've got this 0 and this 1, and then we've concatenated them together. So we have 0, 1, 2, 3, 12, 13, 14, 15. 0, 1, 2, 3, 12, 13, 14, 15. And similarly for the rest of the vectors in each matrix, and thus in each tensor. So 4, 5, 6, 7 goes with 16, 17, 18, and then blah blah blah. And then we get to this, so now we're here, and we concatenate it with the first vector from, or we can concatenate the even vectors from this even index on the first dimension. For every vector in it, we concatenate the vector with its corresponding vector from the odd dimension. Okay, so we see here 24, 25, 26, 27, and then we concatenate it with 36, 37, 38, 39. And by concatenating these, we've built up our context vector. So this is our bidirectional context vector here. So this is what we just looked at was the concatenation of HT in the forwards direction and HT in the backwards direction. Now we do the same thing for the self state because we want to initialize our LSTM or our decoder RNN with the self state as well if we're using an LSTM. We can't do H0 and H1 because this is only going to... Oh yeah, in our specific case we can do H0 and H1, but this is general code, so we can actually, because we have this layers here, which we use in the LSTM. So if you want to pass in more than one layer, if you want to have a stacked LSTM with 2 layers or 3 layers, then this code is generalizable and applicable to that as well. But you're right, in this case we could just do H0 and H1. So dim -1 is from the syntax that Torch uses, and I was doing the same thing in NumPy, which uses axes instead of dim. But yeah, if you were to implement the same kind of code in Torch, you would use dim and not axes. And cool, thanks. Okay, so let's look at the decoder. So do you guys have any code for the dropout, embedding, and the RNN? Whoever's doing this, you're a legend. Thank you. Cool. So obviously we initialize dropout with the dropout probability that we passed in. Initialize embedding to go from hidden dim, I believe, to embedding dim. Yep. To is that right? Output dim and pad IDX equals okay, yeah, that's what I thought. This should be output dim to embedding dim. I believe. Let's take a look. Yeah, so we want to end with embedding dim. So the output of our embedding layer should be embedding dim, which we feed into our RNN. So the embedding layer is output embedding dim, and the RNN. Let's see if that's correct. So we do nn.lstm. And let's look at what we have in our LSTM up here. So embedding dim is going to be our input, and then hidden dim as sorry, I had a bit of a brain fart there. Hidden dim is obviously this the dimensions of our hidden vectors, and then we don't set bidirectional to true, and we'll set batch first to true here. Cool. So we have a feed forward layer which applies the nonlinearity, and we also have like a final output layer which we're going to use, which has the actually, I want you guys to ignore this for now. The reason is this ties into a concept known as weight tying, which is something that when we originally wrote this code we thought we would do, and then we changed our mind, but we trained the models already, didn't have enough time to retrain the models, so we couldn't remove this piece of code. But for now, just think of it as just another linear layer. Okay, so all it's doing is we're running through this feed forward linear layer, and we run through this output linear layer as well. Okay, so let's work on the actual forward method. Yep, cool. Thank you for answering that. So we want to do self.dropout and self.embedding of our input x, and then we need to run the LSTM, and we initialize this to the hidden and cell state of the decoder. Of the encoder rather. So was anybody able to figure out how to do this cell block? Because you had to read the documentation to be able to figure out what to do. Okay, let's see if we can work through this. So we're on the LSTM part of our documentation when this loads. Yeah, that's correct. But we'll take a look as to why that is. Okay, so this is the in our documentation, or PyTorch's documentation. We're at the LSTM
class here. So with these module objects, so LSTM obviously being one of the examples, you'll see 3 of these gray sections here, right? One's called parameters, the other one's called inputs, and one's called outputs. What this is parameters is like the class constructor. So when we define the LSTM object, like here, these are the parameters that this LSTM object can take. So these are the initialization parameters. Then when we want to call the LSTM, so for example here we want to run the LSTM, we want to call it. These are the inputs that we can take, right? So we see these. So you have input and then a tuple of H0 and C0, where H0 and C0 are the tensors containing the initial hidden state and the tensor containing the initial cell state. And if they're not provided, they both default to 0. So we are providing hidden. So here we see hidden is a tuple of Hn and Cn. So what we want to do is self.rnn and have the input, which is sequence length batch input size. So we're batch first, so we batch sequence length input size, which is here. So we do embed, and then we do hidden, because hidden is obviously our tuple which contains Hn and Cn, which is what we want to pass here, the initial hidden and cell state for our decoder. Okay, so let's run the feedforward layer. Guys, what do we run the feedforward layer on? Do we run it over output or do we run it over hidden? Okay, I think the stream is a bit delayed. So we run this over output. Okay. We'll when we run this code, we'll see what the shape of output is, or we'll see how output gets built into a bigger shape. Okay, and then we run output equals self.out output, and we want to remove the one dimension, so so it's output.squeeze. We see the 1 here is index 1, so we want to squeeze this. Okay, cool. All right. So one thing I mentioned was this. So actually, I think output and hidden would be the same here, because here it looks like our sequence length is 1. It's not exactly the same, but they just represent. No, sorry, yeah, the same. Because this is 1, so hidden just takes the. So obviously Hn is going to be the last hidden state of output. So this would just be like the last indexing. So output and Hn are going to be the same thing. Yeah, what was I talking about? Yeah, so I mentioned teacher forcing earlier on, which was this methodology. Now at train time, if we enable teacher forcing, we we make a prediction, but we feed in the ground truth to the next time step as the input to it. So this would be if we had teacher forcing with like a 100% ratio, but we can like have it be a probability, right? So instead of it just being either we use teacher forcing or we don't use teacher forcing, we can say we use teacher forcing, for example, half the time. So 50% of the time we will use the ground truth token as input to the next time step, and the other 50% of the time we'll use the predicted output as the input to the next time step. So for example, for x2 here, the predicted output was researchers, whereas the ground truth was core. So let's say we mistakenly made this researcher's prediction, then at x2, if our teacher forcing, like if the probability of the random number we generate is less than our teacher forcing ratio, we instead of using core, we'll use researchers. Okay, so just keep that in mind when we get to the relevant part of the code. Okay, so we have this Seq-to-Seq object, which is going to wrap our encoder and decoder. Also, we'll do this with attention, but right now we haven't looked at attention, so this is just going to be initialized to false. Sorry, I think you mean squeeze. Yeah, so squeeze is just a very convenient function in PyTorch, which will remove the dimensions or remove something from a tensor where the dimensions is 1. Okay, so if you have something of so we can do this in our terminal, right? So okay, so if I have hn equals mp.arange, we'll do 12, so 2, 3, 4 dot reshape, sorry, 24 and reshape 2, 3, 4. Okay, so if we have 2, 3 or 2, 1, 3, 4 or 2, 1, 3, 1, 4, you'll see that these axes, they come into our shape, but fundamentally because the contents are the same, because this 1 actually adds no information, it just adds an extra dimension, but there's no additional information contained when we have a dimension of 1. So it can remove these dimensions. I don't think there's a squeeze in NumPy, right? But basically what squeeze would do is if we run squeeze, we specify the dimension number that we want to remove the dimension for, right? So the only numbers we can specify in squeeze are where there's a dimension of, or the index is where the dimension is 1. So in this case it will be at index 1 and at index 0, 1, 2, 3. So we do 3. Oh, okay, did work. And we see that now this 1 from the third dimension is gone. And we can also do, so let's do hn equals hn.squeeze1. We'll see what that looks like. Okay, so we see here we had 1, 2, 3, 4, 5 opening brackets, and now we have 1, 2, 3, 4 opening brackets because we've dropped this one of these dimensions. Now we can do 3. Sorry, do 2 because we removed 1. So okay, do shape. Oh crap. Okay, we see the shape, and then we could have removed dimension 1 by specifying hn equals hn.squeeze2, 0, 1, 2. And then we'd get something which is 2, 3, 4. Yep, it's spacey dot python.m spacey download de. Actually, if you look on the GitHub, this is exactly the same as the English one, but instead of en, we do de. So it'll be python-m spacey download de. And remember to run that as admin or sudo if you're on a Unix-based system. No, squeeze is the opposite of unsqueeze. So unsqueeze, you can specify a dimension and add something in there. So if we have hn equals mp.arange24 dot reshape 234. Let's say we wanted to add a dimension in between the first and second dimension. So we do hn equals hn dot unsqueeze, and then we'll say we want to add a new dimension in index 1. Okay, it doesn't look like this has unsqueeze. Might have expand dims. NumPy unsqueeze. Okay, interesting. So it has expand dims. Did I spell it wrong? Oh, okay. mp.expand dims, and then I would probably do, hn and index 1, and then hn equals, or hn.shape equals 2134. Okay, so expand dims is the synonymous thing to unsqueeze and torch in NumPy. Okay. So, yep. So the sequence-to-sequence class is something which wraps the encoder and decoder. So let's look at the forward method. So it takes the source sentence and the target sentence along with the teacher forcing ratio. And then we will create this outputs tensor, which will be the max size of the max length of the target shape. So okay, I just want to check one thing. Okay, right now, when things are coming into this, it looks like they're of size, they're time first and not batch first. So normally would expect batch to be, if we have this HN here, we expect things to be batch. Squeeze this. Okay, so normally when we expect our inputs, we expect them to be of size batch, time, and then dimensions. So the terminology we've been using has been B times T times D. But when we load in the data from torch text, it loads it in as time batch D. So actually, this is 102. This sorry, this is torch. So okay, cool. So tensor.permute 102. Okay, so when we load in data from torch text, we usually see it as T times B times T times B, because we don't have the hidden dimensions yet. So here what we're doing, what I believe is going on is that we have the source input that we're feeding in, and we're taking we're finding the batch size from the second index, and we're taking the max length from the first index of target. So target is the sentence that we want the translated sentence that we want to generate, whereas source is the sentence that we're feeding in. Okay, so we initialize our tensor of zeros. So this is max length times batch size times output dim. So t times b times output dim, and we run our source sentence through the encoder. So in the encoder, we see we have a permute. So it comes in as t times b, so sequence length times batch size, and here we permute it to batch size times sequence length, so it's more familiar for us to work with, but we do that in the encoder as opposed to in the sequence class. So when we're working with source and target here, they're going to be in sequence length times batch batch size shape. Sorry. So now what we do, this little line will initialize the output sequence with SOS. And if you guys read through what this is trying to do, so it says we take the first, same as this actually. So the first word of our target is going to be SOS, start of sequence. So when we load in with torch text, I'll show that to you. But this is what we initialize our decoder output with, right? So this is the start of sequence token, and we're initializing our decoder output with that. I think, yeah, those should be the same thing. Okay, so now we want to decode for token by token, and we're going to look at this else statement here because we're not doing attention yet. So for t in range 1 to max len, where max len is the maximum length of the targets, because this is what we're trying to generate, we run our decoder, the decoder output, and hidden, right? So in the first loop of this, our decoder output is going to be this start of sequence token, and we have this hidden state which comes from the encoder. Okay, so remember this hidden contains hn and cn, so the hidden state and the cell state. So we feed this in to our decoder as initialization, along with the previous word that we're using to that we're going to base our decoding off of, right? So here we're at this point here. So we have this first word, which is start of sequence, that goes in along with the hidden states from the encoder, right? And this will predict some output, and then either we will feed this output into the next time step, or we will feed the ground truth into the next time step as the input to the RNN. Okay, so we return decoder output and hidden. Okay, and then we have this outputs t. So t is our current loop iteration. So for every, so for this first index, so this is what this t is doing. So this first would be 1. So outputs 1 equals decoder output. Outputs 2 equals decoder output, where decoder output is going to be, okay, that's here, so we'll get to that. So we have this teacher forcing thing, which I just mentioned earlier on, where if we meet or don't meet this criteria here, then we either enable or disable teacher forcing. And teacher forcing ratio was defined up here as a half. Okay, so the predicted next token is the argmax of our decoder output. So our decoder output is batch times output dim. So this means we have something which is probably like a vector with 7,000 dimensions, or of length 7,000, where each one of those entries is like a probability ratio that the word is well, what we want to do is we want to take the index which has the highest number in it, because that's what our model was most confident about the word actually being. So this argmax will do that. So this gives us our predicted next token, and what do we use it? Oh, okay, here. So the decoded output is going to be either the ground truth word if the teacher force ratio comes off as true. So if we use teacher forcing here, we're going to say the teeth word of our target is going to be what our decoder output is going to be. Otherwise, we're going to use this predicted next token from our RNN. So it could be here, the teacher forcing ratio might fail, so we use this y hat instead of y. And if it passes, we use y instead of y hat. Okay, and then we have this thing called greedy search, which we're going to use for actually translating. It's very, very similar, so we can take a read through it if you want. But what it's doing is, instead of, we can't do teacher forcing at test time, we do it at train time. So essentially we're doing the same thing, but we're just using this pred next token 100% of the time, because we can only have our predictions to work from. Yeah, so having it around 50%, I think, does help training, which is why we've included it in this notebook. Would you change teacher forcing as an algorithm? Yeah, you definitely could do. That's definitely an interesting experiment to try out. So you start with it being true 100% of the time, and as training progresses, you might be able to you can change the ratio for it to become lower and lower until you can remove it indefinitely. There's nothing stopping you from doing that. Good question. Very good question. Okay, guys. We're gonna take another code break. I want you to get up to this blue section. So, quite straightforward. What we're gonna do is we're gonna load in the data. Gonna show you how the data works. So when we come back, we'll take a look into that. Hyperparameters, building the models, initializing weights. What you guys need to do is set the optimizer. We're going to use Adam. Use initialize the criterion. So you can read here, obviously, I'm going to use cross entropy loss. And try and see if you can search around the documentation to find what this ignore index is and how you would pass it into the loss function. Then I want you to write up how we would load in the source and target data. We need to reset the gradients of our model, run the model, calculate the loss, and run gradient descent. Okay, it's a bit of things to do there, so I'm going to give another 15 minutes. I'm going to give up until 10 to 3 for you guys to do that.
Okay, hello. We're back. It's a lengthy break, so let's run through this code. Okay. Obviously, guys, feel free to post solutions that you've got, and as I make my way down to the relevant part of the code, we can see those solutions as well. So we start by loading in our dataset. So we're going to use this dataset called multi30k, which is a small machine translation dataset. It's actually used for multimodal machine translation, but we're only going to be using the text portion for this tutorial. And as we saw last week, we'll use field and bucket iterator to help us like speed up our pre-processing pipeline. So we'll have a field for source and target where we'll tokenize based on spacey. Our source language is going to be German, so that's why we want to have the German language model for spacey. And our start of sequence and end of sequence token is going to be start of sequence and end of sequence respectively. Finally, we're going to lowercase all of our tokens. We do the same for target as well. Okay, so we'll split this into the training, validation, and test data set. And we'll run this to see how many examples there are. We might need to download the dataset if we don't have it, so that might take a hot minute or a second or two. But we can carry on while this is still going on. All right, we're gonna build our vocabulary, and this min frequency equals 2 means that we're gonna ignore words which have a frequency of less than 2, obviously. Let's do the same for our source and target, and we build this from our trained data. Okay. Define our batch size and our bucket iterator, which will create the iterators for us. So we have the train, valid, and test iterator, and we're gonna print these to have an example of what's in our data. So an example of a source sentence is going to be this German sentence which translates to this target. So a man in orange staring at something, in an orange hat staring at something. So that's these two lines here. And then with padding and with the start of sequence token, so we're just going to see like a start sequence and something at the end of sequence. There's no actual real padding in here because we're only feeding in one Y element. If we feed in more than one Y element, this will automatically pad to the lengthiest input. And then we tensorize, or it's just a verb this in here, so just process this Y, so we convert this from the ground truth into our list of indices. So that's what this target.process does. Okay, so hyperparameters, these are pretty straightforward. We're using hidden dimensions as 512, so quite big in this case. And we extract out the source and target pad token because we'll need to feed this in to the initializations of encoder and decoder, and we build our models, right? So we build the encoder and take this pad IDX and build the decoder where we take again the target pad. Then we obviously build the sequence model by taking the encoder and decoder. Decoder. So should be pad edX. Oh no, it should be capital. And it got an unexpected keyword argument pad IDX. So decoder, this should be capital. And we have this here, pad IDX. So okay, I'm gonna remove this, see if this works. Oh, okay. So that's not where the error was coming from. It was coming from this embedding, because I did this pad IDX wrong. What I needed to do is padding IDX, not pad IDX. So here, this is padding IDX, and now that should work fine. Cool, so that's run. Now what we're going to do is we're going to initialize the weights in our model. So this isn't something that we've looked at before, but so this kind of walks you through how to initialize weights. So why do we do this? Well, it's been shown that that neural networks prefer weights initialized from certain distributions, just as a way to start training. So here what we're going to do is we're going to initialize the weights of our model to be a uniform distribution between -1 and 0.1. So the way we do this is we define a function which takes a model, so m, and then for every parameter in the model, we're going to initialize the data of this parameter to a uniform distribution. So actually, we don't call this as like init weights and then pass in the model. We say model.apply init weights, and it will apply this init weights function to the model. So let me know if there are any questions, obviously. And we have 10.5 million trainable parameters. Okay. Did anybody build the Adam optimizer, and did they manage to run the loss function? This is all things we've looked at before, so hopefully they should be straightforward. So we'll run Adam, and then we pass in the model.parameters, and we have the learning rate equal to 1e to the -3. So we print that. Adam is not defined, so it's optim.adam. Maybe we need to import it. Seq-to-Seq has parameters. Cool. Okay, and then we do nn.cross entropy loss. Here we want to pass in ignore index, and what this means is that we won't calculate the loss when we see this pad token. In the ground truth. So in the ground truth sentence, we will see like the target translation, and then there'll be padding to pad this these values to the longest sequence in the current batch that we're processing. So when we have these pad values, we don't want to calculate loss over them because they're not relevant to the model output. So we'll say we ignore whatever loss would come from, index 7, which might be where the padding starts in the ground truth. So to that, we pass in target pad. So it says when we encounter this target pad symbol, ignore calculating the loss over it. Ignore index. Cool. So write it, and now we're gonna write our train loop. So for our train loop, we iterate over the training iterator, and the input is passed into the model and returns the predictions, calculate the loss, and we backprop and run gradient descent. So we're also gonna be using something called gradient clipping, which I'll look at, which I'll show you in the code in a second. But this basically solves an issue known as the exploding gradient problem, which is kind of the opposite of the vanishing gradient problem, but it's just where the gradients accumulate and they multiplicatively accumulate, so they get so large that they don't provide any real signal to our model. Okay, so we'll load the source and batch. So if we look up here, we've defined, we can see examples of what source and how we call it. So it's .source and .target. lowercase. So it will be batch.source, batch.target, and we want to reset the gradients. So we have our model, so we'll just do model.zeroGrad, and this will zero all of the gradients in our model. And we want to run the model, so this is going to be the sequence-to-sequence model that we run. I believe so. It's a very cool train. Train model, train iterator, optimize criterion. Okay, so our model has been initialized. All we've got to do is run it with the source and target. So this is going to be our Seq-to-Seq model. So in our Seq-to-Seq model, the forward takes source and target. Okay, so we just pass it source and target. And we see here the way that we're going to change our data to feed into our loss function. So we want to exclude the start of sequence token from our outputs, which is why, so remember I showed you earlier on in the sequence-to-sequence model, the first token is going to be the start of sequence token. So decode output, we initialize the output sequence with SOS. Okay, so we want to, when we work out the loss, we want to work out the loss just over the actual words. So we're going to exclude the start of sequence token, and that's why we have the one forward here. And we're going to reshape this to be the relevant relevant shape. So here we've gone from sequence length batch size output dim to sequence length times batch size output dim. Okay, so this is now a 2D tensor. And our target tensor is also 2D, which is sequence length times batch size. So if you're confused why there's this output dim here and not here, then take a look through the cross entropy loss in the documentation, and it explains, similar to the way that we looked at in the LSTM, the shapes that it expects for outputs and for targets. So we run our criterion and with outputs and target. We backpropagate using loss.backwards, and we run gradient descent by doing optimizer step. Okay, this is where we do the gradient clipping. So what we're going to say is here's the model parameters and the gradient clip value, which I'm sure is which we pass in. So it could be 5, for example. We clip the gradient. Okay, so we look at the parameters, and anytime we see parameters which could be like below -5 and above 5, for example, then we will say, okay, if the gradient is 10, then actually no, it's not 10 anymore, it's 5. We'll run this. So the evaluation loop is extremely similar to the training loop, but we just don't backpropagate. So we have the torch.nograd. Okay, so the metric that we use for translation is something called BLEU, Bilingual Evaluation Understudy. Now, I'm not going to run into the details of what BLEU works. This whole image here gives an example and a run through of how BLEU actually works. But it is something that we're going to use to judge the quality of our translation. So, or I guess what you guys just need to know is that the higher the BLEU score, the more accurate the translation actually is. So we just have a helper function here which converts a batch of tensors into text So you can, it's pretty straightforward. You can read through this and identify what's going on. And we have this other function which will actually run the testing. So this test blue model, this test blue function will take in a model, and it will iterate over some iterator, whether this are like a trained data set, a valid data set, or even a data set that we pass in ourselves. It will search based on the source and the target from the iterator, and would be able to, and then it calculates the blue score using this Sacra Blue Corpus Blue method. So, do I have an early stop flag here? Alright, doesn't matter. We're gonna run the model. So for every I in range, so for every epoch, run the train loop, get the train loss, run the evaluation loop, get the validation loss, identify the blue score on the validation data set, print and log all these, and save the best model. So we're not actually going to run this because, as it says, this will take probably years on CPU. So we have a pre-trained model which we're going to load in. So we'll load in this model and we'll run this test blue function, which might take a minute or two to actually run. But we can see how well this model that we've just built actually performs on a real life data set. So literally at this point we've built a translation model. Like, you guys have built a model to do translation. Like, that's awesome. Okay, so we see here our blue score is 16. Maybe not the greatest. Blue scores generally aren't high. So I don't think I've ever seen a blue score over 50, even though obviously 100 is the ideal. I don't think I've seen a blue score of over 50. Either way, so this sequence to sequence is kind of an old architecture. So 16 is something that we could expect from it, and what we're actually going to do is feed in our own text to translate. So got this translation method which takes in a model, process it based on our the field that we defined earlier on, and we do this greedy search to decode our or to run our translation. So we have this sentence. Let's search for what it means. The woman walks in the forest. We're going to run it, see how our model compares against that. Actually, really good, right? The woman is walking in the woods, so definitely along the same lines. If you guys know German, or you can definitely put in some sentences here to try and get to see how accurate the output is, or use Google Translate to translate your own sentence into German and then try and decode it using this model. Okay. We're going to take a 10-minute break here before I run into attention, because I just want this all to settle in your head. And this is going to be, this first run through is going to be quite intensive. So I just want us to come in it with a fresh mind. So yeah, grab a drink, whatever. Just settle down a bit and let's prepare to pay attention and go on a journey. We'll come back at 20 past. Guys, you can use the groups, by the way. So the reason if you're seeing this no people here is because they don't have their webcams turned on. So guys, if you can just refresh the page and enable your webcams, come into the groups, and you should be able to see people there. Talk to them about like what we've just done. Maybe try and make your way through some of this attention stuff. See if you can understand what's going on. We have some nice visuals here, which might be able to clarify one or two things. All right. Anyway, we'll see you guys in a couple of minutes. All right, we're back.
Build a drone product.
Just a search. Yeah, we'll build Google.
Yeah, bro.
Okay. How many guys are here right now? 5. You know what? Maybe we should do this through groups if we got 5 people, and then we can make this a lot more interactive. 8 people. Okay, maybe we can't. All right. Cool. All right. So, gonna talk about attention now. So, what is the problem with the normal sequence to sequence model? Well, what it does is it compresses the whole input sentence into a fixed length vector. So that's the context vector that we looked at earlier on. However, there might be a problem when the input sentence becomes very long, because it becomes hard to compress all the necessary information into one fixed length vector. And the final hidden states, just by the nature of RNNs, will tend to include, will tend to have like higher weighting on recent words, and forget words which have been a long distance away. So this kind of links into the vanishing gradient problem. So rather than using one single fixed length context vector, we have a way where we can access all the encoder hidden states. And it would be cool if we could find a way to say, okay, well, we know what the words that we've already generated / decoded are so far. Looking at these target words, the source words, what word do we need to look at most right now to decode the next word in our sequence? So just visually, before I run into the maths, so what this is saying, we have just this like abstract attention thing, okay? So we'll dive into what this is doing, but what we're saying is, okay, we now have access to each of the hidden states of each word, okay? So instead of one context vector, which we did by taking the final hidden state of the forward RNN and the final hidden state of the backwards RNN, what we're now saying is, okay, well, we have hidden states for every single word. Can we utilize these in our decoding process? So we have this attention module, and what we're going to do is we're going to take in the previous we're decoding for SI, where ith is the ith time step in the decoding process. Okay, so for the ith time step in the decoding process, if it helps to put a number on it, let's say the fifth, for the 5th time step in the decoding process. So this will be decoding the 5th word. We're going to look at the previous decoder time step, the hidden state of that. So this is SI minus 1. So here we have like HT minus 1, you know, to refer to the thing which is before the penultimate hidden state. So here we're looking at the penultimate hidden state, and we're saying, okay, let's look at this along with all the encodings of every word in our source sequence, and find what we need to pay, what word we need to pay higher attention to. And what I mean by what word do we need to pay higher attention to is what word do we need to focus on the most, or what words do we need to focus on the most to decode our next token in the decoding sequence, in the target sequence. So, just looking at this this example here. So we have English sentences on top, French sentences down at the side. And what we want to do is find out for every word which word we need to pay most attention to when we're decoding. Right? So here we generally see this like 1-to-1 ratio because French and English can generally be like very easily one-to-one translated. So like the syntax of a French sentence is similar to the syntax of an English sentence, which isn't the case with other European languages. So the syntax of a German sentence is a bit different to the syntax of an English sentence because they have their verb at the end of the sentence usually. So so here we see like agreement, for example, and it has a high correlation with the word accord. But we get to this place where it's the European Economic Area, and in French, like it's that they obviously have this concept of the European Economic Area, but it has a different word order to it, right? So they say zone economic European, right? So when it comes to the word zone, so this is so we're moving down here, right? So we're decoding. These are our source words, and these are our source words, and these are our target words. So when we hit zone to decode zone, we need to look at the word area, and similarly for economic and European, we're looking at these. We're paying more attention to the words which are relevant to decoding the current word. Okay. So let's talk about how this works, and I think when you guys understand the maths, it'll become a bit clearer. Okay, so we have a decoding time step and a context vector. Okay, so this context vector, this I refers to the ith decoding time step. So we're decoding for the ith time step. So the context vector at time I, is equal to the summation of this thing called alpha. So alpha IT HT. Sorry, this shouldn't say decoding. This should just say a context vector CI is computed as a weighted sum of all encoder hidden states. Okay, so what is T? Now T is what we use to refer to the index in the encoder or in the input, right? So here we have x0 all the way up to xt. So this would be x1, x2, xt minus 2, xt minus 1, xt. So for all t's in T, so for every time step in our sequence length, let's work out something called alpha IT and multiply that by ht. Okay, so what does alpha IT mean? So ht obviously refers to the hidden state at the current time that we're iterating over, right? So this is for every t in our sequence length. Ht refers to the hidden state of that t, right? So if we were t equals 2, then ht would be h2. But what is this alpha IT? So I refers to the current decoding time step, and t refers to the time step that we're looping over. But what it basically is, it's a representation of the relatedness of the source target position at time step t when the decoder is generating the target token I. So the intention behind this is that this is going to be a scalar value, and we're going to scale the importance of that particular ht that we're looking at. Okay, so this is going to be a value between 0 and 1. So if it's close to 0, it means, because this is a summation, right, that our context vector is a summation over our hidden states, scaled by something. Okay, so let's say alpha is 0. That means our hidden state would have we would pay no attention to this word for decoding at time step I. But if alpha is 1, it means, okay, we need to pay a lot of attention to this particular word when decoding at this time step. So this is just a scalar value which indicates for the current ht that we're looking at, right? So for we're looping over these t's. So for this t, how important is this word? How important is this hidden time step to decode our next symbol or our next token? Okay, so how do we work this out? Well, essentially, it's done by a neural network. So it's some alignment function which takes in so this is A, not alpha. So this is alpha and this is A, and A stands for alignment function. And the alignment function is a neural network. So what we're saying is we're going to feed in our previous hidden time steps into a neural network, along with our previous decoding hidden state, along with all of our hidden states. So this is the definition of the alignment function. So the alignment function takes in the previous decoding hidden state and all the hidden states of the encoder, and applies a non-linearity, so that's the tan h, over this this weights matrix times or this weights matrix multiplied by the previous si minus 1, which is just the previous decoder hidden state, and UA of all the encoder hidden states. Okay, so U and W here are weight matrices, and so is V. And I'll talk about V in a second. But what we're saying is, let's run this HT and SI minus 1 through a neural network, and this will give us something called E. Now, the alignment scores are just a softmax over this E. Okay, so E is a probability distribution, which is saying, okay, or if we know what softmax does is it pushes some values higher when whatever score that we've calculated is higher, right? So E is logits. Think of E as logits. So we're running a softmax over logits, and this will scale values between 0 and 1, and also output like a probability distribution. So alpha IT is basically one of these softmax values, right? So this softmax is going to be t-dimensional. It's going to have a length of t, and we're saying we're looping all over the t's here, and we're saying, okay, so for index at t equals 0, we'll take the first element of this alpha vector and multiply that by ht. Okay, cool. I'll run through that visually in a second. Actually, let's do that now. Okay, so just holistically, we have all the hidden states which we feed into this attention module. So we're currently running this attention module over this SI minus 1, so the previous decoder hidden state. So we have a function which takes in all the hidden states and SI minus 1 and outputs a context vector CI. Okay, so let's look at this. Okay, so across the bottom here, we have all of our hidden states. So start of sequence, je, all the way to HT. And we have we have access to SI minus 1 as well, obviously. So that's here. And what we're saying, for every word, for every encoding of a word, we're going to feed it through a neural network, a fully connected layer. So we feed in each HT, so H0, H1, H2, all goes to here, alongside SI minus 1. And this gives us a calculation of an energy score. So, sorry, this one, when it's square here, when we have this one square, I mean that as a scalar value. So these are all scalar values, okay? So we have logits, which are referred to as energy in this particular context. So what we're going to do is we're going to run a softmax over the concatenation over all of our energies. So we have an energy for each particular word given this SI minus 1. Now we're going to put them all together and we're going to run a softmax over them. And this is going to give us our alpha weights. So the softmax obviously outputs a probability distribution with values between 0 and 1. And each one of those values, is represented by alpha t, where t is this indexing here, so 0, 1, all the way up to t, and then we multiply that by the original hidden state of the word that we passed in, okay? So this alpha is going to be multiplied by h0, this alpha 1 will be multiplied by h1, this alpha 2 will be multiplied by this alpha t is going to be multiplied by ht, and then we're going to add all of them together, and this gives us our context vector ci, okay? So that was, you know, quite a mouthful. Just going to wait here for like a minute or two to see any questions rolling in. Cool, no questions. Awesome. Alright. So, one thing that I didn't mention was this VT, or VA, rather. So, all that means is that this neural network here is going to put something to, let's say, hidden state dimensionality, and then we're gonna run this with another weights matrix, which will put this down to 1, which is obviously representative of our scalar value. So this will make things to be in to return the scalar value. Okay. So we have our self.w, and we're going to initialize this to be 3 times hidden dimensionality. Now, while I run through this code, I want somebody to type out why it's going to be 3 times. Why is it 3 times hidden dim? And we're going to return something which is hidden dimensions. So this is this neural network here. So everything that I've highlighted, this tan h and in these brackets. And then we have another neural network which will take this hidden dimensionality. So this is a v, and we'll put it down to 1. Okay, and this will give us our e, each of our e's. Okay, so here's what we take as in our forward method.
All right, we have the decoder hidden state. So this is Si minus 1. And we have all the encoder outputs. So that's all of the H's. So H0 to HT. Okay, we're just going to permute this to be in a shape that we can work with a bit better. So this is going to be batch times 1 times H. And what we're going to do is we're going to repeat this for source length times. The reason we do this is so we have things in a shape where we can matrix multiply them together. So remember when we looked at RNNs from last week's lecture? I'll open that up and we can see how these are similar. Okay, so if you recall, the formula for working out the hidden time step of an RNN is some 1 weights matrix times the previous hidden state plus W times the input. Now, for computational efficiency and a small trick that we can do, which with neural networks is equivalent, is we can actually just have one weights matrix and concatenate these variables together. So what we can say is we have like one weights matrix, let's say Q, and we multiply Q by the concatenation of HT minus 1 and XT. So that's because the weights matrix we learned during training, it's functionally the same as doing this. Okay, so we can, instead of having these two weights matrices, we can have one weights matrix and just concatenate the actual variables together. So you see, this is a similar kind of setup. So instead of having a W weights matrix and a U weights matrix, we can concatenate, or we can have one weights matrix and concatenate this SI minus 1 and this HT together and multiply them by this one weights matrix. So here we concatenate SI minus 1 and all the HTs along the last dimension, which is this. And we run self.w, which is this linear layer, and we apply a tan h, which is our non-linearity over it. So this takes us, this does up to there, not the v, but up to the tan h. So here. Okay. So the reason we had to repeat this for source length times was because we need to concatenate the same shapes together. And since this was one, we needed them to be the same shape to put them together. And this gives us our energy scores. And now to work out, to get our attention scores, we run it through self.v, which will actually, these give us logits, and then we run it through self.v to give us our energy scores. And we run a softmax over this, and this will give us our attention vector, which will be of t dimensionality. Don't see any questions coming through, guys. This is quite complicated stuff, so please do ask questions. Okay, so to actually implement this, all we need to do is replace the decoder, and we'll implement the attention mechanism on the decoder part of our module. So I want you guys to take 10 minutes maybe, read through this code and implement it. I've done the attention part for you. Everything else you can look into the decoder. It should actually just be this initialization method, which you guys need to fill out, and the embedding things. Might be a couple of things here. No, okay. So this is the last thing. We're meant to finish at 4, so I won't start on the transformer. But we'll run through this code and then we can call it a day. I think we finished a bit early because I was expecting a bit more questions coming through. Here we go. Full promise. Yeah, so the attention module definitely has a higher number of parameters. Do you mean like class of parameters here? Because we saw earlier on how our normal sequence-to-sequence model had 10.5 million trainable parameters. in this particular case, the bidirectional RNN has the exact same amount of parameters. The only new parameters that we're learning are the parameters of this this attention module. So this encoder part stays exactly the same. So we don't actually have more parameters on this encoder part. We just have the parameters of this attention module. My blue variable test output test blue. There's no attribute called score. You might be on a different version of Sacred Blue. Can you try updating the package? If not, if that doesn't work, then let me know, and I'll do a bit of googling to see how we can modify this function so it does work. And guys, if you saw I refreshed the page and I saw these new questions, but I don't see the old text come up, so I don't know if my chat froze or anything and I missed a bunch of questions. But if I did and you still have questions and I haven't answered them, then yeah, definitely copy and paste them back in here and I'll get back around to it. Okay, so let's initialize dropout, and then .dropout of our dropout ratio, and the embedding, so nn.embedding, and this goes from output dim to embedding dim. The reason we have this called output dim is because output dim and input dim are actually the same, and we were going to use this weight tying methodology here, which we haven't got around to removing yet. Okay, one thing I want you guys to... okay, yeah, sorry, that's quite irritating. I didn't realize that it froze, so I'm sure I must have missed a bunch of questions.
I'm reporting the bug now.
Sorry?
I'm reporting the bug now.
Okay, cool. So yeah, sorry about that, guys. Definitely copy and paste your things here. Yes, there are two classes of parameters. We have we have a weights matrix, and every element in this matrix is a parameter. So you know what we had was 512. You know, we defined our input size to be... Our input size was 7,855 by 256. So just this one embedding layer has 7855 times 256, 2 million parameters. Okay, and then we add you know, plus 256 times 512 plus 1024 times 512. And then we do the same for the decoder, add it all together, and this gives us our 10.5 million trainable parameters. So yeah, we have a weights matrix for the encoder, and for the, like, you can think of it being as like one giant weight matrix, but it contains all of the parameters which the sublayers within it contains. Sorry, how do I find out the version? It's a bit of a noob question.
LS packaging.
Okay. No. Like that, or... Oh. Pip sacre bleu. Uh, 1.4.4. Okay, tell you what, if you can downgrade it for now, and then I'll make a note of that to upgrade upgrade it to the latest version and fix whatever API issues that we're having. So yeah, sorry about that. Okay, so guys, I want you to answer this question. Why is the input size to the LSTM embedding dims plus 2 times hidden dim? So this is this decoder. So this is, you know, the RNN. Why is it embedding dim plus 2 times hidden dim? Okay, remember this is a bidirectional RNN, so each one of these are going to be 2 times h. What is the size? You know, to answer this question, you'll need to think of what is the size of this decoding vector, what is the size of this CI vector, what is the size of this embedding vector, and what is the API for an LSTM. So what shape does it expect to be in these first 2 arguments? Sorry about those messages not showing up. Harun's or somebody is running some tests on here. We're gonna sort that out soon. Okay, so let's run Dropout on embedding. And then we work out the attention scores. So what we do is we pass this we're feeding into this in the forward method of attention. We're going to feed in x, which is going to be our inputs, hidden, which is going to be a tuple of the hidden state and the self state from an LSTM, and all the encoder outputs. So this hidden 0 refers to just hn, so we want to just take out this hn from our hidden, and all the encoder outputs. And unsqueeze it in the first dimension so we can work out C. Now the way we work out C is we use matrix multiplication. So this is essentially equivalent to doing a dot product between an alpha vector and all of the hidden states. And that's what we're doing. So we have this batch matrix multiplication. So we take the attention scores and we batch matrix multiply it with the encoder outputs, and this gives us C, our context vector. Then we run our RNN. Okay, so to run our RNN, what we're taking in as input is we're right here. So this is the RNN that we want to run. We have this CI and we have this embedding as well. Okay, so we're going to concatenate this context vector along with the embedding of the previously outputted word, and that's what we're going to run our RNN against. So here we do the concatenation, and obviously we feed in the hidden, and we get our output and hidden. Then we run the output. So again, this is something to do with weight tying, which ignore it for now. But we just run this output layer. So this is this part here. Okay, again, this takes in CI, so this takes in the context vector along with the previously decoded word, the embedding of it. So this differs a bit from. Whew, we've done a lot, guys. From this part here, because here we only took in the hidden state. Now we take in the word, the context vector, and the hidden state. Okay, so we have 3 inputs into this neural network: the word embedding, the hidden state, and the context vector. So here we have the context vector, the embedding of the word, and the hidden state. And we run this through the linear layer, which gives us our output. Then this output has something to do with wait time, so we can ignore it. We squeeze our dimension, and we return output, hidden state, and all of our attention scores. The reason we return the attention scores is so we can plot them. Okay, so let's run this. Okay, here we're just gonna build our encoder and decoder again, initialize the weights as we did before, initialize our optimizer and our cross entropy loss. So now we see, previously we had 10.5 million, now we have 13.5 million trainable parameters, and this is because of everything that's going on in the attention decoder. Okay, so you can, to the guy who's asking about the question about parameters earlier on, you can take a look through this this code here, and you can work out the number of parameters and try and find out where, which part of here, the attention part, these are the additional parameters that having attention in our system adds. Okay, so it's our train loop. Again, I'm not going to run this because it'll take absolutely years to train on a CPU. I'm going to load in the pre-trained, the model that we've trained for you on exactly the same code. This will take, again, a minute to actually run. And in the meantime, I'll show you what the rest of the code is. So we can now translate an actual German sentence into English. And we're going to plot the attention matrix like what was shown up here. So we do this by getting the attention weights, obviously, so we pass in attentions here, and wherever we call plot attention. Okay, and so our attention weights come from this. We run the model, so we get here output and attention. So this attention comes from this model.greedy search. So if you go back up to the sequence model that we defined near the beginning of this lecture, you'll see that there's a with attention flag. And if we have this with attention flag, we return the attention weights. So, okay, yeah, so we basically take the attention weights and then we just pass them into our plot attention function, which will plot them according to this code here. So run this, and then we can, translate that same sentence again. So we see, like the massive increase in our blue score by adding attention. Previously we had like a blue score of 16, and now we're on 36 with attention. So I'll run this, and we can kind of see the attention plot map. So woman makes sense with Frau, and we can kind of see this like 1-to-1 ratio going on. And the reason why this is here is because of the syntactic structure of German. So this word "wold" is looking back, and we see, okay, we need to look at the word "the" to see what it refers to. Although weirdly, I would expect there to have been something in here. So I will definitely take another look at that, because it's oddly low. Okay, this wraps up this lecture. Yeah, so let's recap what we've done. While questions come in, so guys, feel free to ask any questions. Obviously, see if there's anything there. Okay, so we looked at how or the different ways that you could formulate a bi-RNN depending on the task that you have at hand. So if you have classification task, you'd want to take the last hidden state in the backwards direction and the last hidden state in the forwards direction, concatenate the two together. You have a sequence-to-sequence task, and you want to access each of the hidden states for every input. We would concatenate the relevant cells of the backwards RNN and forwards RNN. Alright, we then looked at the sequence-to-sequence model, the context vector in particular, and how we can use the LSTMs and RNN knowledge that we have to build a translation system. Then we looked at the issues with it. There's a lot. And spoke about attention, which is a methodology that we can use, which allows our model to look at certain words and understand what words it needs to pay more focus to when decoding the next word. So we looked at the math behind it and we implemented that. Hopefully that's a bit more intuitive now. I think the important thing to realize, this diagram kind of breaks it down. These E-scores are scalars. Sorry, these things in with one square, they're scalars. Just keep that in mind. And then we actually implemented the attention mechanism. We ran it, we saw our new blue score, and we did some translation stuff with it. Okay, cool. This brings us to the end of the lecture. I'll stick around until about 5 past, answer any questions. You know I'm always accessible on Slack or WhatsApp, so feel free to drop me a question there if you want to ask something which might not be entirely relevant to this lecture. Okay, guys, apart from that, it's been a pleasure teaching you. Hopefully, I'll see all of you back next week, where we'll be looking at the transformer. The transformer is the state-of-the-art translation system, which currently underpins all... Well, it's the algorithm which currently underpins all state-of-the-art translation systems. So really exciting stuff, you know, cutting-edge state-of-the-art stuff that even the likes of like Google and Facebook are using. Awesome. In a bit, guys.